Hi friends, we are discussing about various aspects of MOSFET. Today we will see about body effect. In our previous discussions, we hadn't considered the voltage applied to the substrate of the MOSFET. We have just taken that the source and the substrate, the body, is shorted. In today's video, we will see if we are considering the voltage applied to the substrate, what are the variations that come into picture? Let us see what the body effect is in case of MOSFET. For that, consider the simple structure of a MOSFET. We are having a P substrate and source and drain is N plus region. Now we will, in our earlier discussions, we were assuming that the source and the body B, the source and the body B is shorted. Now we will see if it is not shorted, what happens to the action of the MOSFET. For that, we will just ground the source. Since we are not trying to plot any MOSFET characteristics, we are grounding the drain also, and we have the gate connection where we will be applying the gate voltage. The center portion, as you all know, is similar to the MOS capacitance that we had seen earlier, MOS capacitance, MOS capacitor. And if you remember, we had defined a term threshold voltage, which is the voltage that has to be applied at the gate so that inversion happens at the channel. Or in mathematically, VGB, the gate voltage, becomes the threshold voltage when we are having inversion. In order to have inversion, psi s should be equal to 2 phi f. Now let us consider the first case where VSB is equal to 0. Here you are not applying any voltage, it is 0. At equilibrium condition, which means before applying any gate voltage, the band diagram will be of this fashion. We are having a concentration of electrons at these 2 points because of the source and drain, and the central part, which is a MOS capacitor, will have the band diagram like this. The intrinsic energy level is above the Fermi level by Q phi f. Now when we apply the gate voltage, when we apply a gate voltage, the inversion happens when the gate voltage is equal to the threshold voltage, and the band diagram will be in this fashion, which shows that the energy band level is coming down and the intrinsic energy level is now below the Fermi level by the factor Q phi f, which means from Q phi f above Fermi level, it has moved down the Fermi level by Q phi f. So that we are having 2 phi f. That is what the inversion happens. That is when the inversion happens. So this is the band diagram when the gate voltage is applied. Remember, this is the normal scenario when no voltage is applied or VSB is 0. Now suppose a negative, the VSB is made negative, which means a positive voltage is applied at VB. A positive voltage is applied at the VB. Now, let us see, the intrinsic energy level is below the Fermi level when we apply a positive voltage at the body or the substrate, which means that now the gate voltage required to bring in this condition, bringing inversion, that voltage will be lesser, because already the intrinsic level is beneath EF. Now, only thing is that it has to be brought down to the fact that it should be phi f beneath Fermi level. So, the required threshold voltage decreases when there is a positive voltage applied to the body or the substrate. Now, when we make VSB positive, that is by applying negative voltage at the body or the substrate, the energy band diagram is of this fashion, where the intrinsic level, you can see, is above the Fermi level by not only Q phi f but also the VSB, the voltage that is being applied at the body. Now, in this case, the threshold voltage Vt should be more, because you have to bring this part beneath Fermi level, so that you have to apply more voltage. If directly, if we look, the voltage that you should apply more is equal to the applied VSB. This can be mathematically written as the threshold voltage Vt is equal to VFB, which is the flat band voltage considering all non-linearities, plus 2 phi f, which is the voltage that you have to bring it down, plus root of 2 q epsilon, the permittivity of the semiconductor, Na into 2 phi f. Earlier it was just 2 phi f. Now we have this factor plus VSB divided by the capacitance COX dash. So, if we take case by case, when VSB is 0, this term, this equation is the new equation for the threshold voltage after considering the body effect. When the VSB is 0, this term becomes 0. So, it becomes a normal threshold voltage. When the VSB is negative, we require only a smaller threshold voltage, or the voltage to be applied at the gate is lesser, so as to bring in the inversion. And in case of the third case, when VSB is positive, that is been added on to this term, so that the required voltage to bring in inversion becomes more, or the Vt is more. So, this is the effect of the voltage applied to the body of the MOSFET. While we were discussing in the earlier cases, we were not considering this factor, and the add-on voltage or the increase in threshold voltage due to the applied voltage to the body is called, this effect is called the body effect, also known as bulk effect or substrate effect.